Welcome to Engineering Mechanics, Statics, Chapter 8, Friction, or more accurately, a very brief introduction to friction. What are we going to talk about? Well, in preceding chapters up to this point, we're making one of two assumptions, right? We're either assuming that two surfaces in contact with each other are perfectly smooth or frictionless, or we assume that these two surfaces in contact with each other are what we call rough, which means that the stuff, no matter how hard you push, the things will not move. Well, obviously, neither of those two cases exist, right? There's no such thing as a perfectly frictionless surface. So whenever two surfaces are in contact, tangential forces, which we're going to call friction forces, will develop if one attempts to move relative to the other. Okay, however, the friction forces, they're limited in magnitude, right? Friction can only resist so much, and eventually things will start to move. If you apply enough force, it will overcome the frictional force and it will start to move. So that means that really to talk about the difference between frictionless and rough is really, it's a matter of degree. So what do I mean by that? Just by way of example, if you're trying to push around something, say it takes 1,000 pounds of force to push something around, and the friction that we're dealing with in that situation is say 2, 3, 4, 5, 10 pounds. Then you know what? Who cares? It's so small that it's relatively unimportant. So you could kind of call that a frictionless surface. The other extreme, right? You have something that you're dealing with on the order of say 1 or 2 pounds, and once you get up near say 100 pounds, then it starts to actually move. Well, you know what? You can call that rough because it's not going to move with the forces that you're dealing with. But in general, the more general answer is that to say that something is either frictionless or rough is really doesn't make sense. It's going to be somewhere in between. Okay, now there's two types of frictions. There's what's called a dry friction or Coulomb friction, and there's what is called fluid friction. So fluid friction specifically applies to lubricated mechanisms. Oil, a piston cylinder in a car has oil in there, right? For this class, we're going to gratuitously ignore that. We are going to talk solely about dry friction between non-lubricated surfaces. So thus the very brief introduction to friction for this chapter. Okay, so the laws of dry friction. Let's talk about dry friction. So say we have a block. We have a block here, has a certain amount of weight, sitting on say a table. Okay, so this weight is pushing down. Well, there's a normal force responding to this, keeping it from moving, right? And that normal force is N. Well now, so there's no friction force here, right? But now we're going to apply a small force here, P. Try to move it across the table. Well, as you apply that small force P, there's going to be this frictional force F that will be created. It's gonna arise, right? If this is not there, if you have a force P here and there's no frictional force here, this thing's gonna move. Okay, so in the real world, you have some block on here. You start pushing on it. It doesn't move at first because a force. There is a force that is responds to that P, and it's a friction force. And this is specifically what we're going to call the static friction force. Now, as P increases, the static friction force is going to increase as well, right? So here's our little, this is P. As you move up in P, your friction force is going to respond, and it's going to be a 1-for-1, right? If you're pushing on it with 10 pounds and it's not moving, it means that you have 10 pounds of friction preventing it from moving. If you push on it with 20 pounds, then if it's still not moving, then you're going to have 20 pounds of friction. And eventually you're going to hit this maximum value Fm, and Fm is found by the mu sub s. The mu is what is called the coefficient of static friction times the normal force. So this is the maximum friction force. This is this point right here. So eventually you're pushing on it with just this much and it still doesn't quite move. And if you push on it with even the slightest bit more, boom, it starts to move. Okay, and then once it starts to move, you get into a different range, and it's called the kinetic friction. And that kinetic friction value, Fk, is mu sub k times the normal force, right? So it's and you'll notice it's going to be less. And everyone, I think, has found this in just real life, right? You're trying to push a cabinet or a couch across the ground. It's harder to get it moving than to keep it moving. Once you get it moving, then all of a sudden the friction drops a little bit and you're dealing with the kinetic friction, which is less than the static friction, and then you can keep it moving. Okay, just by way of just kind of a reference point, here's some approximate values. This is from the book. Approximate values of the coefficient of static friction on dry surfaces. So you're ranging between say 0.15 all the way up to say 1.0 or to 0.9. Now the maximum static friction is found by mu sub s times normal. Again, this is not just the friction. That's the maximum that it can do to resist motion. It's the mu sub s times the normal force. The kinetic friction is mu sub k times the normal force. And as a rule of thumb, mu sub k is approximately 75% of mu sub s. So you usually have like a 25% drop off. That obviously can change, and they do different things depending on what you're doing with. Sometimes you want this to be a lot smaller if by design, right? So you don't get kind of a jerky effect. But in general, the kinetic friction tends to be about 75% of the static friction, the coefficients of those. So the maximum static friction force and kinetic force are A, proportional to the normal force, right? So you have this Fk and Fm. You have some number and you just multiply it times the normal force. So they're proportional to the normal force. They're dependent on the type and condition of contact surfaces. Hopefully everyone has that sense, right? You stick a hard metal thing on ice, and it's going to move in a different way. It's going to take a whole lot less friction than if you stick wood on wood. Say, his example over here, you're talking in the range of 0.25 to 0.5, right? If you have two sheets of plywood on each other, and you start to try to push them, it's going to be a lot harder to move those relative to each other than it is, say, a nice little block of metal or steel on a thing of ice, because the coefficients are definitely different. And the last thing is that they're independent of contact area. The friction is going to be just this. It's mu sub s times the normal force. We're not going to consider the contact area in this. Okay. 4 basic situations can occur when a rigid body is in contact with a horizontal surface. And 4 is really misleading. It's really 3 and then one special one that we'll talk about. First off, you have some sort of block. It's on a surface, and you push down on it, right? So there's no lateral forces, nothing here that's trying to make this thing move. So the friction force is 0. Fair enough. Next case, we start to push on it a little bit to the side, right? This P force starts to have a little bit of Y and X values. Well, the normal force is going to increase, right? The normal force, just like over here, is P plus W is the normal force, right? Here you're going to have Py plus W is the normal force. And you're going to have some friction force. And that friction force is going to be equal to an opposite of this value Px. So in other words, if it has a tendency of, say, 10 pounds to move to the right, the friction force is going to be 10 pounds to the left. Or if not, it moves. And then you work your way to this motion impending. And this is the one where it's this is really just a particular case. This is not its own situation. It's just that moment right before it moves. So at that moment right before it moves, then you're just at that point where you have your maximum static friction, and that's given as mu sub s times the normal force, right? That is that point where it's just about to move. And then lastly, you start to move, and then all of a sudden your frictional force becomes mu sub k times normal force, and it's less than your force. That's why it's moving. Now again, this one over here, it's not its own thing. It's just an instance. It's part of this situation over here. It's just that it happens to be that limited factor right at the very end. Now, sometimes we want to replace this normal force with a friction force, the normal force and the friction force by the resultant R, right? So here, the resultant is just straight up. Now you start to push it a little bit, and all of a sudden you'll see that this R starts to push, that you have this is the frictional force, and this is the normal force, and so the reactionary, or the resultant, is there. And then you have, again, this motion impending one, which is that special case. Now here we know something that's kind of cool. It's kind of unique to this situation. If this is motion impending, it means that we are at the maximum frictional force that it can do. Well, what is a maximum frictional force? It is mu sub s times the normal. So you notice if you look at this angle right here, the tangent of this angle is opposite over adjacent, right? So it's going to be Fm over n. So Fm over n. Well, Fm at that moment, just before it starts to move, is mu sub s times normal over normal. So obviously the normals cancel out, so the tangent of phi sub s is mu sub s. So it's kind of a cool feature but this is only true at motion impending. And then you start to move, again, just like the other ones. So now the phi becomes phi k, because it's kinetic, and so you have, so this should be a k. Tangent of phi k is all this stuff. It works out to be some mu sub k. So that's kind of a cool situation. Cool thing that you can look at. Okay, so that that's, you know, you have forces, you have resultants, angles of resultants. Well, another thing that we can do is consider a block of weight, W, resting on a board, and that board is being tipped up, right? So again, back to this. Pretty boring, same thing, right? No friction. But now all of a sudden you start tipping this thing up. Well, what happens when you tip this up? Well, the weight's pushing down. This downward has a certain portion that's perpendicular to the normal, to the surface, right? And that's going to be the normal force. And then you have a portion that's parallel to this, or what I've been calling a lateral force. So this is going to want to slide down. So there needs to be some sort of amount of friction to keep it from sliding down. And again, you get that motion impending, and now the thing that's unique about this motion impending, you can figure out these phi angles, and it's called the angle of repose. It's that phi sub s, where you're at that limit before it starts to move, and then boom, it starts to move. Then all of a sudden, your reactionary force, your resultant force, is at an angle. It's no longer in line with the W because it is moving. So when we're doing these friction problems, there's basically going to be 3 basic types of problems. Okay, one problem. You're going to have all the applied forces. You're going to know what all the forces are. You're going to know the coefficient of static friction and or the coefficient of kinetic friction, right? And then your job is going to be to determine whether the body will remain at rest or slide. So you look here. Okay, so we have this block that has some weight. Without this force and without friction, this thing's going to slide down. But now I'm pushing this force. Okay, so now is this force enough to overcome this thing want to slide down, or does it want to go up? Now, but we have also this friction because this force is adding to the normal force and whatnot. So that's going to be your job, to figure out what this wants to do. Another scenario is going to be when all the applied forces are known and motion is impending. And why would we do that? So, well, we can do that to determine the coefficient of static friction, right? So you have 2 surfaces that you're dealing with, do a little experiment on. So you go and you slowly lift up the board. You have the known weight, and you just lift up the board until you at a known angle, and you measure when it starts to move, right? And so you can figure out the coefficient of static friction. And the last option is, you know the coefficient of static friction, you know motion is impending, so we determine the magnitude or direction of one of the applied forces, right? Saying how hard can you push on this before it starts to move. Those are your 3 basic problems that we are going to be dealing with when we're dealing with dry friction. So let's do some of them right now. We have 2 example problems. We're going to do example 8.1 and example 8.3. Okay. Just a little summary here. Friction. It only exists when there's a force, or at least a component of the force, parallel to the surface that something's resting on, right? If there's nothing trying to move it across relative to each other, there's no friction. Now the maximum static friction is, we're going to call Fm, it's mu sub s times the normal force. Again, this is the maximum that it can resist. It's not the friction at any point in time, it's the maximum value that it can resist. The kinetic friction is mu sub k times the normal force. And remembering that mu sub k is roughly 75% of mu sub s. Again, that can change, but that's a good rule of thumb. Now, if a lateral force is less than Fm, the maximum static friction force, then the friction force is equal to the lateral force, not Fm. That is one of the most common mistakes that everyone makes, is you go through and you figure out, hey, this thing can resist up to, say, 60 pounds of force. Okay, so now I'm pushing on it with 40 pounds of force. Therefore, my friction force is 60. No, my friction force is the 40. It's the value that it resists. It's not the maximum value. So basically, when we're solving problems, the first thing we're going to need to do is determine if the lateral force is greater than Fm. So if there's a force that's greater than the maximum static force, then you know if it's moving or not. If it's moving, then friction is actually relatively easy. It's F sub k, right? So it's a mu sub k times normal force. If it's stationary, then the frictional force is whatever that lateral force is. It's not Fm, it's whatever that lateral force is. And that is friction. So we're going to do some homework and we'll be good to go.